Hello, my name is Jose Palacios, and I am an associate professor of aerospace engineering at Penn State. And I also have the great pleasure to lead the adaptive structures and noise control section of the Center for Acoustics and Vibrations. Thank you very much for taking the time to assist and participate in this conference. And I would like to go ahead and jump right away on sharing some testing and modeling we've done for what we consider an adaptive structure for ice protection of fixed wing configurations. The title of the presentation is Modeling and Experimental Testing of a Hybrid Impulsive Pneumatic De-Icing System. And this work was conducted by my former student, Carter Forey, and myself. And we had the pleasure as well to work with Invercon LLC, which is a small business that got funding from the Air Force. So on that note, let me go ahead and flash you the legal disclaimer on our funding acknowledgement. And once again, thanking Invercon and the Air Force for the grant that provided the funds to conduct this research. So the presentation outline today, it's going to go over the background and motivation for the work, and then I'll go through the objectives, the modeling conducted, some of the experimental verification using finite element analysis, and then we'll move on to correlations between the models and the experiments. And then I'll jump to a full-scale testing demonstration and conclusions. So background, the background could be summarized in a sentence. Flying on icing is not a good thing. And what that means is that when you fly through a cloud that has super cool water droplets, these droplets will impact on the surface and accrete. And these ice formations will be very detrimental to your aerodynamic performance. So what happens is the liquid water content, LWC of the cloud, or the medium volume diameter of the droplets, will create different ice shapes as these vary. So if you increase LWC, MVD, or velocity, you will move from rime ice to glaze ice. So what is this rime ice and glaze ice? On this photograph on the bottom, you can see a very nice example of glaze condition, which will give you a shape that is basically not following the aerodynamic shape of the airfoil. This is obviously quite a bit of drag and penalties on the thrust or lifting. You could have hybrid, or I would say combined ice shapes, which will have some features of rime conditions and glaze conditions. And then you will have rime, which are ice shapes that are formed as the water droplets freeze on impact on the surface. Therefore, they follow the shape of the airfoil. Do not believe that this will give you low drag. The ice roughness is pretty high, and it still will give you quite a bit of penalties on the drag on that airfoil. So now that we've seen that ice accretes to airfoils, and we've seen that you can get different icing shapes depending on the conditions of the cloud, let's go ahead and summarize the penalties as everything gets bad, okay? Lift will increase, the weight will increase, the drag will increase, and your stalling speed will also increase as you are decreasing your thrust capabilities. So you can see some photos here of the mess, and notice that this leading edge area has a black cover on it. This black cover is actually a neoprene pneumatic system that inflates and deflates to break off the ice so you can maintain flight. Even with that de-icing system on, you can see quite a bit of ice attached to this neoprene structure, which I should mention has very high adhesion strength for the ice. That's why it requires upwards of 150 PSI to get rid of these ice shapes. Another photograph here, you can see how there are lines of ice. That's because these booting systems have different areas that are inflated, and they break off the ice in chunks. But still, even with the de-icing system on, these accretions are quite severe. And you can see here a in-flight ice accretion shape, which we can see that is a glaze regime. So now that and this will be an example of rime, okay? Once again, not like it's gonna give you lower drag because the roughness is quite high. So with that, let's go ahead and talk a little bit about pneumatic de-icing systems. They've been around since the late 60s. And as I mentioned, these are different areas that are inflated with pressures up to 150 PSI. And that's where you will get those lines of ice formation, right? Because on the nodal conditions of these bags, the ice does not debond as easily as on the antinodes. And once again, these boots are typically made of neoprene, which is great for erosion and also flexible enough to be inflated. But the adhesion strength of ice to neoprene is quite large. So you need up to 150 PSI to debond this ice, which is obviously quite a bit of energy. So in the past at Penn State, we have explored replacing these neoprene bags with metallic leading edge structures that are a single cavity. What does that mean? Now you're going to get rid of those nodal conditions where the ice didn't break off that easily. If you want to introduce additional stresses, you can also introduce span-wise segments under that cavity. And this research was conducted maybe back in, I would say 2014 or so, and was mostly catered for rotating structures because the pressures we used were actually created by the centrifugal pumping of the rotor itself. I don't want to go into the major details on that, but the point is that we demonstrated that this single cavity inflation was possible in terms of removing ice accretion, and also created a much higher erosion resistant leading edge than neoprene, because neoprene is okay for fixed wing. But if you will put neoprene rotor that has tip speeds reaching Mach 0.7, those neoprene boots will get chewed up. So you will require an isotropic material such as stainless steel. So that's somewhat of the background of the technology. The modeling that was conducted for these single cavities was only static in nature. So only static pressure was applied into the finite element analysis conducted. We did not have any dynamic or inertia effects included on those models. And I'm just showing you here an example of model results where you can see the nodal separation of your elements. And when I say nodal separation, that will be the separation between the ice accretion nodes and the nodes on the accreting surface. And on the x-axis, I have the normalized wrap distance. So as this nodal separation exceeds a certain value in micrometers, the cohesive failure mode analysis that I will describe in a second will predict either ice delamination or not. So with that, let me go ahead and jump on to the objectives of the work that I'm showing you today. The objective is to introduce a novel hybrid impulsive pneumatic de-icing system. And what does that mean? We do not want to inflate these cavities statically, meaning that the pressure increases are quasi-static. We would like to hold the surface down until a certain pressure is reached, and then release all that energy onto the leading edge, creating a sudden impulse that will assist with the delamination process, as we will demonstrate. In addition to that, we want to make sure that the model that we're going to develop basically compares favorably with experiments that will be conducted on a flat plate. And this is almost we're also going to use the experiment to tune the model, because as I will explain, these cohesive failure modes are highly empirical. Once we have this model and tests correlated, we're going to move on to modeling and testing a airfoil structure under impact icing conditions. These will be realistic conditions, as you will see in flight. Once we have the model of these smaller airfoils conducted and verified, we will move on to a full scale test that I will showcase at the very end. So with that, let's go ahead and introduce the model briefly. This model can be found in many different literature documents available. Some of them actually developed by our team and specifically related to ice adhesion strength testing. But in a nutshell, what you have is you have a structure that is being pulled apart. On the top, you will have your ice, and on the bottom, you will have your surface. So you can see that the stresses, as you move from point 0 to point 1 to point 2, will not have delamination until you reach a certain value. And then as you reach that value, you will move on to points 3, 4, and 5. So on the vertical axis, you have the stress on the graph, and on the horizontal axis, you have delta, which is the nodal separation between the upper bonded material, ice for us, and the bottom substrate. So if we look at some of these equations, notice that at point 2, this is where the damage initiation will start. So T will be your interface tensile strength, okay? And KPs will be the relationship between those stresses and deformations or displacements between the nodes. Now, as you move on to point 4, okay, this is where you start having failure. You're losing the capability to carry stress as you did between points 0 and 2. The G's in these equations illustrate the fracture energy, which is observed during the testing, because all of these properties must be determined experimentally and then introduced into the finite element modeling. Then from there, we could go ahead and introduce a quadratic failure criterion to combine the tensile and shear capabilities of this bonding and determine what would be a mixed failure mode separation between the nodes that will give you debonding. So the ultimate goal is to determine what's my critical separation between the nodes at which I lose the capability to carry stress. And that will equal the lamination of the structure. So with that brief definition, I would like to point you to a literature paper that will give you all the details on how to experimentally determine all of these properties such that they can be imported into the finite element modeling. And you can see that on top, Bailey et al. And we conducted this experimental testing of ice adhesion strength characterization of properties required for aluminum. And you can see that the damage initiation following this quadratic criterion gave us some values for the strength for the modes 1, 2, and 3. And notice that mode 2 and 3 are assumed to be the same. And I'll show you what those modes are in a second. These are the standard modes assumed for fracture mechanics. So in addition to those, we had to determine as well what were our energies, okay, the G's that you can see in this table, as well as our cohesive surface moduluses, which are the K's that you saw in the prior equations. So these material properties, once again, are experimentally determined and then imported or inserted into our finite element modeling for cohesive failure modes. So with these numbers, we end up with what we really wanted, which is what's my critical node separation that will give me the lamination between ice and aluminum in this case. And that number is 6.88 micrometers when inserted into the equation. So with that number now, we can go ahead and run cohesive analysis using Abaqus. And here we can see an image of the different mode failures, mode 1, mode 2, and mode 3. And by inserting those values in the finite element analysis, we can end up with graphs that look like this. Vertical axis, nodal separation, and horizontal axis will be your wrap distance between points 0 and 1 along the leading edge of the airfoil. Notice that if the nodal separation exceeds that 6.88 micrometers that we calculated as being critical, we can predict that the lamination will happen. If you are below that number, then the ice will remain attached. So in this graph now, I'm showing you mode 2. Notice that you will have different displacements depending on which mode you're analyzing. In reality, as we introduce pressure to this leading edge, you will end up with a total combination of mode 1 and mode 2, which will give you that black line shown in the graph. Okay. And once again, remember that the failure separation was given by that value of 6.88 micrometers. Above the red line, the lamination. Below the red line, that means the ice will stay attached. And obviously these numbers will change as you increase or decrease the pressure applied to that leading edge cavity. So before we continue, I must mention that you must always check your meshing capabilities and how they become convergent, okay? So you have to determine what's the element size required to reach such convergence. So in addition to that, this cohesive submeshing is very finicky, okay? Because what happens is as you change the mesh size of your model, the model will give you different results. And it's not always the case that the more meshing you conduct, or the smaller the size, the more accurate the result will be. There's a critical element size that will match your experimental results. So tuning these parameters is quite critical. And in addition, you also have to introduce viscosity into the model, because all the energy that you're going to release as the crack propagates must go somewhere. If you run a model without any viscosity, it is very difficult to reach a convergent result. So for our experiment, for our analytical work, we introduce a very small amount of viscosity into that interface. Okay, so with that brief explanation of our finite element modeling approach and how we determine the properties required experimentally, we can move on to testing flat plates first. So as we have discussed, we're using Abaqus as our finite element tool, and we want to model not only the static buildup of the pressures under the airfoil, but we also want to introduce an impulsive release. So we want to hold the airfoil down until a certain pressure is reached, and then release all the energy to propagate ice delamination. So we also have to model impulsive behavior. So we did this analysis for stainless steel leading edges. The reason we didn't want to use aluminum is because aluminum, first of all, it will oxidize. So the surface of the aluminum will change with time. And in addition to that, aluminum is not a great erosion resistant material. Typically erosion resistant materials used are stainless steel, titanium, and nickel. So we went with stainless steel, and you can see a schematic here of the plate modeling. We have two, what we call tabs. These will be the areas that hold the plate down before it is released. Then we have a patch of ice that is 3 inches wide, and the plate width is 11 inches. The plate thickness is 0.03 inches. And these are the boundary conditions applied to the finite element analysis. So, and also here I'm showing you the boundary conditions, which is basically a bolt pressed against a hyperelastic material that creates a sealing cavity such that we can pressurize the plate. So once again, notice that we did mesh convergence based on stress-strain relationships. And from these results, we decided what was the best element size to conduct our modeling. And we ended up with having elements for the ice of 0.86 millimeters and elements for the plate being 0.25 millimeters. So notice that we will have some static analysis, but after the static analysis, once the plate starts inflating, because we're holding it down with these tabs, once we release the tabs, we will have a dynamic behavior, which we model using implicit dynamic steps in Abaqus. And then we move on back to a general static step. When we have a asymmetric release of these tabs, right? Because we have two tabs, we could release them both simultaneously to have a symmetric behavior, or we could have an asymmetric response by releasing one first and the other one later. Then you will have to run two implicit steps between the two general static behaviors. So I want to show you just an example of what this looks like after we run the model. Okay, as time goes by in the x-axis, you will start having some increase of your nodal separation. As you reach a certain time, you will release the tabs, and now you see a dynamic response that will give you quite a bit of separation between those nodes. So let's go ahead and show you some results for a 0.2 inch patch of ice. Once again, normalized distance on the x-axis and nodal separation on the vertical axis. And notice that as I increase pressure, so on the graph right now is 1 psi, and I'm showing you the static, the symmetric release, and the asymmetric release. When the pressure goes up, now all of these nodal separations increase. And also notice that the asymmetric release at these lower pressures is fairly comparable to that of the symmetric release. But once you increase the pressure to a certain point, the asymmetric behavior quite exceeds the nodal separation reached with respect to the static and the symmetric behavior. And this trend also continues as the pressure increases. So having that in mind, we can almost already conclude that asymmetric behavior or asymmetric triggering of these tab releases will give you much higher nodal separation, therefore delamination capabilities versus using symmetric approaches. So here we see a schematic of the experimental configuration. Once again, let me remind you that we're using stainless steel. And to create these tabs, initially, we just decided to use electromagnets. Now, these are only for research purposes. I will explain that the actual system that we introduce in a full scale configuration uses a much lower weight and lower profile approach. But I'll get to that once I reach that point. For now, we just have two magnets that allow me to maintain this plate or hold the plate down as I'm applying pressure. And we have a pressure sensor to characterize that pressure. And we have, like we said, a neoprene, or it is a neoprene gasket to create a sealed structure under this plate. So as we increase the pressure inside of the plate, we use an LVDT to measure the deformation. And we have correlated the predictions to the experimental results, as you can see in this graph. This is the center plate deformation versus the applied pressure. Notice that on the area or in the region of interest, which goes up to 1.6 PSI or so, we have a very good correlation between the prediction and the experimental results. Notice that if we graph the plate deflection versus time, the Abaqus prediction provides a much larger response than the experimental work. And the reason being is that we are not really modeling the drop in pressure that we have experimentally. In the model, the pressure is maintained at a constant value. However, on the real experimental work, as these tabs release the plate, there's a sudden pressure drop, as we can see in the top graph. And that's not captured in the model, explaining the discrepancies between the experimental and modeling results in terms of plate deformation. So let's continue with the experimental setup. To create the ice patch, we basically made a little pool, and we filled the pool with distilled water. And then we went ahead and compared the required pressures for ice delamination versus different ice thicknesses. And we compared the experimental results to that obtained with the finite element analysis. And we saw quite a bit of a discrepancy between the modeling and the experimental work. As you can see on those graphs, looking at the difference between the blue line and the modeling black line. So what's the situation here? Well, it comes down to the fact that we had the wrong cohesive surface modulus, because the modulus we used was that of aluminum. We have a stainless steel. So we had to, once again, empirically determine what would be the proper modulus to match the experimental results. So once we did that, we basically found the cohesive surface modulus that match our nodal separation requirements. We went ahead and introduced such modulus into the modeling, and we were able to get a better correlation between the predictions and the experimental results. And once again, the goal here is to create an engineering tool that we can use to model the system that we're trying to design for a full-scale test coming up. So from this model that now we have been able to match experimental results on a flat plate, which by the way required increasing the cohesive surface modulus by 17% with respect to aluminum, since we have a stainless steel, we went ahead and started designing our airfoil configuration. So for the models, once again, we went ahead and modeled the ice layer. We modeled the stainless steel leading edge cap. These are the properties used for the stainless steel cap in the model. And these are the properties used for the ice also on the finite element model. We have a neoprene gasket sealing the leading edge structure, and we'll have the capability to pressurize it. So if we look at the meshing, once again, we must always confirm that we have convergence on our meshing size. And here we see that we reach convergence once the element sizes become smaller than 4 millimeters, which is what was used for this modeling. And also we implemented our static and dynamic symmetric and dynamic asymmetric approach on the finite element structure. And I'm just showing you here an example of what these results will look like. Once again, vertical axis, nodal separation. Horizontal axis is your normalized distance from 0 to 1, wrapping around the leading edge. Static behavior clearly gives you much smaller separation on those nodes that you will obtain with symmetric and asymmetric responses. Obviously, that graph will change as the pressure increase or decrease. So we constructed this airfoil. Notice that we have these big magnets to hold that leading edge cap, and I hope this don't scare anybody, because for the actual configuration we used on the full scale testing coming up, we held down the leading edge cap using actual pneumatic pressures as well. So it was a very thin extra gasket that had suction rather than pressure. And we were able to integrate this system on the top of an existent Reaper wing, introducing a variation on that airfoil shape of less than 0.5 millimeter. But we'll get to that one. For now, we have this airfoil that holds down the stainless steel plate, which is the leading edge, using magnets. On the image, you can see the pneumatic lines sending pressure into the cavity. Okay. And this is the final product, which has your deformable stainless steel shape with your neoprene sealant and the input of the pneumatic pressure to the leading edge section. This will be a side view. You can kind of see the magnet through all that bonding mess we had to do for the neoprene. Okay. And we control those electromagnets via a computerized system. In this video, you're actually seeing how the pressure is increasing and how we just released the electromagnets such that you got an increase in airfoil shape. We placed the airfoil into an icing wind tunnel that we have available at Penn State, and we introduced representative aircraft icing conditions. And the tests were conducted at -10 degrees Celsius. The reason is because -10 degrees Celsius was the temperature used to characterize the properties needed to conduct the cohesive analysis. So -10 degrees Celsius, we accreted ice for the amounts of time given in these different columns, and we had a speed of 35 meters per second. So in this graph, we have the required pressure on the vertical axis versus the leading edge ice thickness. And you can see that the required pressure will increase as the ice thickness becomes smaller, which makes sense because the transfer shear stresses that you can generate under a thicker layer of ice will obviously be greater than that under a thinner layer of ice. Something very clear to observe here is that the asymmetric behavior decreases the pressures required versus the static approach, which, by the way, we're not able to provide delamination under the pressures provided in this research. As we know, static deformations will require very large pressures. Our maximum pressure was around 3.5 psi. Once again, not sufficient for static deformations. So from this result, we can also say that once we exceeded around 0.25 inches of ice, the ice delaminated, of course, but then it was impossible to actually remove it from the structure. What will happen is you will have a delamination of that ice cap, but then the ice cap will stay floating on the leading edge and pressured against the leading edge of the airfoil by the aerodynamic forces. The reason is because now you have a very high bending stiffness on that ice shape that even though it delaminates, it does not fracture, so it does not come out of the airfoil. And we're gonna see that on the videos. So let's look at case 3, one of the cases where the ice thickness is less than 1/4 inch. So the video is going right now. You have ice accreted, pressure is applied statically. Now you're releasing magnet 1, now magnet 2, and you see how that small deformation was able to crack the ice shape and debonded from the leading edge of the airfoil. Now let's go ahead and move on to case 4, where the ice thickness is greater than 1/4 inch. Once again, pressure is being applied. You're applying pressure right now. Now in 2 seconds, you're going to trigger magnet 1 and magnet 2 right now. And you can see that the ice, it is delaminated, but the shape of the ice did not fracture at the leading edge. Therefore, it became a cap floating on top of the structure. And you can see that cap here on this photograph. This was basically just, the tunnel was stopped and you can pretty much just pick the ice right from the airfoil. So when we compare now these experimental results to finite element analysis, we saw that the prediction told us that only 84% of the ice will debond if you look at how much nodal separation you have over that red line. Now, we saw that the entire ice came off. So what are we missing on this finite element prediction? Well, the finite element model doesn't account for material cohesive failure, doesn't account for asymmetric drag that you will have on these ice shapes, vibrations, or unsteady aero forces that might affect the shedding behavior. Now, if we focus on just one of them, let's just look at the drag, okay? The drag on that eye shape can be determined based on the shape and aerodynamic analysis. So basic analysis will tell us that we have these drag coefficients on those eye shapes. When you introduce these additional shearing forces on the modeling, now you see that 95% of the acrylic eyes will debond, agreeing closer with the experimental results we just saw. When we go ahead and summarize these results, we see that we have an 18% difference between the finite element analysis and the experimental test conducted on this airfoil. And we see that the fracture eyes cases have larger percentage differences than those cases that have thicker eyes. And once again, we capture the trend nicely of the required pressure versus the leading edge eye thicknesses. So with these tools now, we had the capability to design a system that could be tested on a full scale configuration. And that system was designed, fabricated, and tested at the NASA Glenn icing facility. I'm not going to go into the details of the design since it is somewhat proprietary by the business, but let me explain that magnets were not used. The system was fully pneumatic and it was very thin profile, and it combined pressures and suction to maintain that leading edge cap down. So as mentioned, we went with a full scale. This is actually not a Reaper wing, but a Predator wing that was installed in the NASA icing wind tunnel. And we conducted many tests, but here I'm just going to showcase one of them, which is also a negative 10 degrees Celsius. And you can see the video coming up. The video is sped up. Okay, this is going much faster in time than the actual test. So now you see the system is off. Okay, you can see ice accretion. And as you turn the system on right now, you can see how the asymmetric excitation of the leading edge clears off the ice formation. We can maybe see this video again. Once again, ice is forming on the leading edge of that wing. And now the system is turned on. And the leading edge is cleaned very well. System is off right now. As the ice thickness becomes critical, then you are able to remove all the ice formation. All right. So in conclusion, we have developed an impulsive methodology that is more effective than de-icing using static configurations. This allows you to use isotropic structures that are single cavities versus multi-cavities. We have demonstrated that this is possible using stainless steel, and we have developed the moduluses required to conduct finite element analysis using stainless steel. And we were able to match these models with a 18% difference with respect to experimental results obtained on airfoil shapes. In addition to this, we used these models to develop a full-scale design that was tested at the NASA Glenn icing facility. So with that, I believe maybe questions might be submitted later on. Thank you again for taking the time to support our center and for coming to this conference.